Okay, so today, after the test that everybody took yesterday, we're gonna pick up where we left off from Tuesday, which is on the mineral PowerPoint. Actually, let me go back just a little bit. I do have some rocks that I'm gonna show you today. I've got some examples that we're gonna go through and a couple extra website pages because sometimes these PowerPoints aren't the greatest. They should have a lot more pictures in them. And actually this year, I guess today, I will start maybe inserting another slide or two to try to beef up my PowerPoints and make them a little bit better for next year. So maybe I'll try to remember to do that. Okay, let's see. So we're starting off here with luster. Yesterday we went through some different mineral traits, and we kind of got to this point where we're really going to start to talk about the different characteristics of minerals. The first one is luster, which is essentially how it reflects light, or in a general sense, how it shines, like what kind of shiny it is. The easiest ones to get are going to be metallic lusters. They just shine like a metal. You know how a metal shines like nothing else shines, whether it's like the legs of your chairs or chrome bumper or metal from a piece of jewelry or ring. You don't have to feel it or touch it or scratch it to just be able to look at it and be like, that is a metal. May not know what metal it is, but I know that that's a metal. So they kind of have a shine all its own. It's difficult to describe it other than to just say it's a metallic shine. And so if it shines like a metal, that is a metallic luster. Now, know that if you pull a metal out of the ground, the very few metals that come out of the ground or in rock form that actually shine like a metal. And so we also have a submetallic luster, which is essentially a dull metal that doesn't shine, but because you feel it, you know it's heavy, you test it with a scratch test, you're pretty sure it's a metal. Metals kind of feel different than a normal rock. And so even if it's not shiny, it could fall in this submetallic category. I'll have some pictures of these in a second. But here, we really get into terms that are very subjective and sound very loose. And this is why I've made comments about geology being, I don't know the proper term. It's not like a loose science. Like, it's very scientific, but some of the terms we use are not scientific. They're very subjective. So like glassy is very easy. If something looks glassy, you should be able to see that it looks like a piece of glass. It has a glassy shine. But what does earthy look like? What does pearly or silky or greasy look like? Yes, yeah. These things are very subjective, and obviously on anything in nature, nothing really, some things do, but most things don't really fit perfectly into categories. It's a wide scale. And so you could have things that you're like, is this dull? Is this earthy? I don't know. It could be either one. And that makes geology somewhat, in some instances, very subjective, especially when you're getting into minerals and rocks. And you'll see that later in the rock categories. But I do have a nice picture. Let me go out of this. Sometimes there's a bar up here that allows you to minimize, and sometimes there's not. Now my button's not working. There we go. So I pulled up a nice web page, not this one. Here we are, which has some pretty good examples of some of these. Know that these were kind of curated to fit into these categories nicely, and so it's good for an example, but when you actually see real life samples, they don't always look exactly like this is. So we start off with metallic. This is a nice shiny piece of metal. It's probably, it might be galena, but galena also usually has a nice shape to it, and I don't see that here, so it could be something else. But this is a metallic shine. Obviously, the picture is not the greatest, and I had to blow it up to get bigger. But you can see that it has kind of a metallic shine to it. Where you move into the submetallic, and it just kind of looks like a black lump of rock. There is some shininess over here on the edges, and I will tell you this is probably easily metallic. If we get something like, I think I passed it around in yesterday's class. That's not metallic. Not yesterday's class, but Tuesday's class. Let's see if there's something in here. Yeah, that's got a little bit of a shine to it. But like this rock here, I'm going to turn the light on real quick. I don't really want to pass it around, but this one, especially that side, it's not very shiny at all. It just looks like a black lump of rock. If you get it just right, you might get a little shine on it, but it does feel heavier than you would expect a rock of this size to feel. And so this is probably a metallic rock. And if you did some other tests and it confirmed that it was a metallic rock, you could call it submetallic in luster. That's kind of hard to get to, but some of these things are hard to get to. It's very subjective, and sometimes you have to figure out other things before you can fully place it in one category or another. Then we move to adamantine and vitreous, which are just two different words for glassy. I would say that adamantine is going to be more of, and you can see this in the picture, more of like a crystal type shine than your just standard glassy, which will kind of have a little bit less transparency. It's still translucent. You can see light through it, but not quite as transparent and not quite as shiny, where the adamantine will be very clean and bright and shiny to it. But these are kind of two very similar lusters here. Vitreous definitely stands in the glassy category. I think most quartz, if you're familiar with quartz, and we will see plenty of it, I think, in a little bit, not today, but soon. Quartz always falls in the vitreous category, a nice glassy look. Resinous, the best example I have for this is if you ever had like a little figurine or something that's made from resin plastic. It has a very particular shine, but it's like a plastic shine, not like a hard glass or like a metal shine. It's just shiny like plastic. It's opaque, and it looks different from anything else. That's the resinous look, almost like a plastic type shine, even though it's not plastic, it's a mineral. Then we move on to pearly. Pearly is actually a pretty good description. It's going to look like the inside of like an oyster shell or a clam shell, or like a pearl. So it's going to be opaque, no lights coming through it. Usually it is these whiter, lighter colors, and sometimes you can even kind of see that pearly sheen, which has more of the rainbow into it instead of just one single color. The rest of these get a little bit more subjective, but I will say, if you were to pick up any one of these samples, these like really nice, perfectly curated samples, you would probably see it instantly. Like this rock, when you pick this up, you would not only see that it looks greasy, it would feel greasy in your hands, which helps out a little bit. It's just the way the rock is, the minerals, and the way it kind of rubs across your skin. It has that greasy look and feel to it. And so if I told you before you saw this picture, before you saw this rock, that a rock was greasy, you'd be like, what is he talking about? But when you actually get them and see them, they're pretty rare. There's not a lot of things that fall in this category, or any of these last four other than dull. Dull's pretty common. Any of these last three here. But once you do see one, you're like, oh, that's the greasy rock. That's the earthy rock. That's the silky one. So greasy here, I hope you can kind of see it from the picture in the way that it's shining and kind of bulbous. That's a nice greasy sample. Then you go to dull. You're going to find a lot of stuff that's dull. Anything that's not metallic and not shiny is going to probably fall in the dull category pretty easily. And probably even stuff that could normally be pearly or greasy or earthy could also be considered dull. It's like a blended together scale where you can kind of have a little bit of each. But dull, you're not seeing any shine. There's not really smooth surfaces. It's just a dull mineral is what it is. Then you get to earthy, and earthy and dull are sometimes very hard to tell apart. I would say you almost have to feel the earthy rock to be able to distinguish it from dull. It feels a little bit more clay-like, and that's the kind of term that I'm going to give. Very, very small particles, probably not a very hard rock in the earthy category, and you can kind of feel it in your hands that it definitely feels like a piece of dirt in a way, or you kind of get that the texture of something kind of coming off in your hands. And so that's the earthy feel. I'm not positive, but I think like talc, which we'll talk about in a little bit, talc would probably fall in the earthy category. And then at the end, we get to silky. This is actually a really, really good descriptive term for these rocks. Silk comes from single strands from the silkworms, right? And so it's very much strand-like. when you get these rocks, they have fibrous filaments of minerals. So we'll talk about crystal growth and cleavage in a little bit, but the minerals grow in single strands. Now, this is a rock filled with these single strands, but you can see that they're aligned in this direction. And so this silky sheen very much comes from those single strands of minerals that are fibrous, like serpentinite, which they use to make asbestos. So, I didn't want that to happen. So let me go back to the PowerPoint. That is your luster. Know the difference between opaque, which means you don't see any light coming through it, and translucent and transparent. Translucent means you do have light coming through it, but you can't really see things on the other side. Transparent means that, like, if I set it down on a piece of paper or on a newspaper, I can actually see the stuff on the other side. Like I could read words through it. That's transparent. Oops, let me go big screen. Now, color. I'm not going to spend a lot of time on color. We all know what color is. Just know that for some things, color can be really helpful, but for the vast majority of things, color's not going to help you out very much at all. It might help you eliminate a couple things, but you can see here that fluorite has these 5 colors that they're showing you. Fluorite can be almost any color. Quartz, on the other hand, can be almost any color. And you can even see that this quartz looks very much like this fluorite outside of its shape if you're just looking at the color. Very similar. You've got like brownish red. Here's a black. That's more like a dark purple. But there are some minerals that can be almost anything. And it doesn't matter what your mineral is, other than a couple rare ones like gold. If you've ever seen gold, there's nothing else that looks like gold. Not in the entire world. Even when you get into pyrite, which is fool's gold, they don't call it like, almost gold or tricky gold. It's fool's gold because it doesn't really look anything like gold. And if you've ever seen the two side by side, you'd be like, how did they get that mixed up? It's not the same thing. And like sulfur, sulfur is that like bright yellow color. I guess I'll go ahead and pick this up. It's like a bright yellow color that really nothing else gets this color like sulfur. That's not transparent. It's not like a crystal. It's an opaque rock, and it's really unique in the mineral world. Other than that, like when you get into greens, browns, blacks, blues, there are lots of different minerals that can fall into that category. So color can help you out. It's part of the puzzle of you figuring out what mineral you have in front of you, but very rarely will you just be able to look at the color and be like, that's this mineral. So moving on to streak. Streak is a different type of color. Streak is the color of the mineral in powdered form. And so what we have, if I get over here, nope, put it up here, here we go. What we have here are called streak plates. These are little porcelain plates, a porcelain tile. It's pretty hard. It's like a 6.5 on the Mohs hardness scale. And what we do is we take the mineral and we scrape it along this plate. We have this. And where none of the minerals go, here we go. And I'm going to do my hematite. Hold on one second. I'm always misplacing things. Well, hopefully it doesn't fall in that hole. Well, do I have another piece? All right, well then fine. I'll just use the pyrite and not the hematite. Do I have something else that will work? Hematite's not going to do it. Okay. I see how it is. Still don't believe it's not like right here somewhere. As soon as y'all leave, I'll find it. Probably fell in that hole. Okay, anyways. I'm gonna turn the light on. Here we have a streak plate. A lot of streaks will look just like the mineral. It just depends on what it is. There are some really, really nice ones that turn out very different. And so what I have here is a nice piece of pyrite. You can see the shiny kind of gold look, but not like the mineral gold, just the color gold. Pyrite's one of the ones that forms a different streak. And so if you were thinking just on color, if I scratch this on the plate, I should get something that looks kind of like the color that it is, like a gold. This is actually going to come out nice and black. So the way you do this, don't hold it in your hand. These don't break very often, but if it did break, you don't want it to break in your hand. So put it down on the table, take your mineral, push down a little bit, and scratch it. It might sound bad a little bit, especially when you do the glass plates. But you can see, check this out. Or don't, whatever. You can see it's a black streak. And so it doesn't come out gold. You do get a little bit of the pyrite flecks in here that make it shine just a little bit. But that's definitely black. And I had a hematite, I don't know where it went. But hematite, what does hematite sound like?
Hemoglobin.
Yes, it sounds like hemoglobin. And what is hemoglobin in? Blood. Yes. And so hematite, the rock sometimes looks red, but a lot of times it's nice and black colored. It gets this really deep, like blood red streak to it. I'm really disappointed that I misplaced it. I wonder what I did with it. Anyways, hematite gets a really, really deep red one. And so these streaks can actually be super, super helpful. They will help you eliminate different minerals as you're trying to figure out what mineral you have in front of you in a lab. The only catch is, let me turn this back off. A lot of minerals have a white streak. They just leave behind a white powder. And seeing a white powder on a white plate isn't necessarily the easiest thing to do. I'd never seen these before I came here, which is actually kind of crazy because I went to OU and they had like the geology department is one of the richest departments at OU. They have like the tallest building on campus and all the money. And they didn't have black streak plates. And so when I got here and we had them, I was like, oh, this is great. Because there's a whole bunch of minerals that make white streaks. And so if you have a nice black streak plate, you can see the white streak and you can know whether it's a streak or not. At the bottom here, they do mention not all minerals produce a streak. The ones that don't produce a streak are the ones that are harder than the streak plate. So the streak plate is like a 6.5. If I have a harder mineral like a diamond and I scratch it on the streak plate, it's not going to leave like powdered diamond behind. The diamond's just going to leave a scratch in the streak plate, and that's not a streak. So the ones that don't produce a streak are harder than the streak plate itself. Now, crystal shape and habit. And when we get to cleavage, I will kind of like, you'll see that it is difficult sometimes to see the difference between a crystal shape and what is cleavage. They're both made from the same concept, which is these form from the way that the atoms connect together on the molecular level. Cleavage is when they break apart. Crystal habit or shape is actually how they grow together. And we will use that term crystals growing. We'll also use it in igneous rocks. It's a good term. Like it sounds misleading because growing is like a biological term. But crystals very much grow. They start from a seed crystal, very small, maybe just a couple molecules large. And they have to build outward slowly over time. And so the larger your crystal is, the longer it took to grow. And so they very much do grow. But the way you have crystal habits is basically from the concept that depending on what atoms you're hooking together to make your molecule, you'll have different molecular shapes. And depending on your molecular shape, there's only so many ways you can connect a bunch of those molecules together to make a pure mineral, and that will dictate what shape the overall mineral is. And so you have these tetrahedrons, which actually are pretty versatile. They can make a lot of different shapes, but they're like a triangular pyramid, like a three-sided pyramid, although the fourth side would be the bottom, so four-sided pyramid. You have cubic molecules, you have linear molecules, and depending on how those molecules form together, they will grow in different shapes. And when we get to cleavage, you will see they will break in very specific ways sometimes. And so crystal habit is very much how the molecules connect together and how that crystal grows. Both of these are pyrite. Pyrite actually is one of the minerals that has quite a few different crystal habits. There might be a little bit of everything in this one, but as I flip the lights on, you see that this one is very much just like a random rock. Like you can see the shininess of the pyrite, And if you got it under a microscope, you might see some cubes. There's a couple in there, but a lot of it is just pyrite kind of just smashed together. So it can grow in like a massive form. Anytime it doesn't have a straight crystal shape, we call it massive. It can grow in these flat discs that kind of radiate outward in strands, single strands. They call those, I forget what they call them, but they look like sand dollars kind of. They grow in these cubes, and you can see I passed around the cube in the last class period of pyrite, the like nice little square. If anybody wants to see it again, just let me know. But these are cubes, although there's like several of them and they're all kind of intertwined. This is more like a soccer ball shape. I don't remember the exact name of it, but you can see there's 5 sides to each of these little pentagons that make up the side of the soccer ball kind of shape. And so depending on, they're all the same molecules, but depending on how they start to form at the very beginning, all the other molecules that build on the outside of that have to match that pattern. And so it's kind of a randomness at the beginning, but afterwards, it really has to continue to grow in that specific way. And so that is crystal habit. They're going to show you some examples here. This one is fibrous, and this is what's associated with that silky sheen. This one does not look very silky because they got a really nice sample to show you the fibers. But you can see the like vertical, linear growth habits, and then you can see on the side the fiber stuff coming out. This is serpentinite. They call it that because of its green kind of color and because of the fibrousness that comes off. This is the mineral that was used to make asbestos, which, as you all should know because of the TV commercials from lawyers, asbestos is really bad for you. And if it gets in your lungs, it causes permanent lung damage because these little fibers are parts of the rock. These rocks have been around for hundreds of thousands, if not millions of years. And so when they get in your lungs, your body's not able to break them down very easily and get rid of them. They embed themselves in your lungs, and it causes lifelong health problems. And so we use this a lot in the beginning as a building material for insulation. But now we know a little better, and if your building does have asbestos in it, it's really expensive to get it removed because the people that come and remove it have to have a lot of personal protective equipment, and you have to dispose of it in a proper way. These are bladed. This is probably gypsum. If these are labeled, I would almost guarantee this is gypsum. Start small, kind of comes outward and gets bigger and bigger as it comes out. And if you kind of see the ends of these in profile, it looks like a sharp, like elongated diamond shape. So very much like the blade of a knife or the blade of a sword. Down here you have cubic crystals, which are like the salt that we saw, or like the pyrite. And so they grow in a square formation because of the molecules and the way they fit together. And this, I would argue, does not belong on this page. Banded is not a crystal habit or shape. Banded is a way that your mineral grows sometimes, but it's more due to the presence of water. And it's not like there's nothing about the molecules that make it grow in this way. It's more just how it grew on a stalactite or stalagmite or inside of a hole in a rock that was filled with water. And so maybe inside of this, you could see some crystal habits or shape. But usually crystal habit or shape, you have exposed sides and you see the overall shape, which this does not really fit into. So maybe that's one of the things I'll change on here. Next, we get to tenacity. I'm going to skip this slide. This is very much associated with hardness. Tenacity, in all of my 6 years going through college, we never talked about tenacity. It's more of an engineering term. So if you get into geologic engineering, basically analyzing what's underneath the ground, how well it's going to hold up your building, so you don't get like a Leaning Tower of Pisa kind of thing. Then you get into tenacity and how well rocks keep from shattering and breaking. We don't really deal with it too much in normal geology, and I've never really covered it very much. It's easily associated with hardness. So hardness is a much better way to describe this, and it's much more understandable. So remember, hardness is a mineral's resistance to scratching. It's not its ability to not break. It's more just associated with scratching. So the hardest mineral is going to be what? We all know it. Diamonds. Note that when we use diamonds in industrial purposes, it's always in a scratching matter. We diamond plate saw blades, which essentially scratch their way through another material. We diamond plate buffer pads or sanding pads. We don't ever diamond plate hammers because the second you smash that hammer on something hard, the diamond's just going to shatter. And so don't think of hardness as like impactability. Think of hardness as scratching and how well it can scratch other things. So we measure hardness on a scale of 1 to 10 called the Mohs hardness scale. I would encourage you to think of Mohs from The Office, which is hilarious. But yeah, the Mohs hardness scale. And how we get to this point to figure out what it is on the hardness scale, we determine it by rubbing the mineral that you have against other minerals or materials that we know the hardness of. And they give a couple examples here. Your fingernails are a hardness of 2.5 on the Mohs scale. I will note for guys and girls, if you happen to have press-ons, those are plastic and will be slightly different from your fingernail. Not too bad, but just be aware of that. Copper pennies, which I thought I had a bunch of copper pennies, and then during first period, I was looking through them all, and they're all from like the 2000s. So know that pennies used to be copper back in the day when copper wasn't that expensive and pennies were worth something. Now pennies are literally almost worthless, and copper is actually pretty expensive. And so we don't make pennies out of copper anymore. And just as a little side note, don't be surprised within your lifetime we just get rid of pennies altogether. They'll just stop making them. We might still have them, but nobody will use them, and they will go the way of the past because pennies are really costing us more money than they're worth right now. So if you have a copper penny, its hardness is 3.5. If you have a newer penny, it's probably slightly harder than that, but not like extremely harder. But we do have some pennies over here in the test kits. Glass is a hardness of 5.5. We also have, I'll grab them before I go to the next slide. We have some nails in here, like a couple metal nails, a couple like metal staples, and if you have a pocket knife, that'll be on the next page too. Don't bring a pocket knife to school. But if you ever need one, I have a couple here in class that we can use. So here's the Mohs hardness scale with matching minerals to the numbers of the Mohs hardness scale and some intermediary tools that we use to determine. So, excuse me, the one thing I want you to know about the Mohs hardness scale, you're usually just looking for a range. Very rarely will you be able to say this mineral I'm holding in my hand is an exact number on the Mohs hardness scale. Usually you will have to scratch it against other things and get like a range. So for example, I'll start at the bottom and work my way up. Talc is the softest one. It's a 1. What do we use talc for? Yeah, talcum powder, baby powder. Because it's literally so soft you can just crush it and it turns into a really soft powder. Yes, yeah, don't use it in your private areas. It's not good. They
babies or as makeup.
Yeah, it's not good for you on your body. Put it in your shoes, maybe. Put it on your hands if you. I don't know why you'd put it on your hands. Maybe just to feel better. Yeah, gymnastics. There you go. Or maybe baseball or something. But yeah, don't use it excessively for long periods of time for sure. But yeah, talc is what we use to make talcum powder. And if you ever feel a piece of talc, it will feel very soft and very smooth. It's actually crazy because you think you're picking up like a rough rock and then you grab it and you're like, wow, this is actually pretty pleasant. So talc is very soft. Next you have gypsum, which is also soft. Note that both of these are softer than your fingernail. And so if you pick up a rock and you think it might be one of those two, just try to scratch it with your nail. You have to push down a little bit, but not too hard. But kind of scratch back and forth. And after you scratch anything, wipe it off a little bit and see if the scratch is actually there. Because sometimes it's hard to tell what you're scratching or what is scratching what. So if you can wipe it off, it didn't actually get scratched. If you can rub it a little bit and the scratch is still there, then you actually scratched it. So take your fingernail and give it a good rub, and it should scratch gypsum and talc. Now, you get your fingernail, and above fingernail, we get calcite. We will see calcite in the lab more than likely. Calcite is a pretty common rock. It's the main constituent of like a limestone, which is calcium carbonate. And so this is the one thing, and we'll talk about this later, that fizzes with acid. And so if you drip acid on calcite, it will start to fizz and bubble, which is pretty rare. So you can help use that to identify some things. But basically, like if I scratch something and my fingernail doesn't scratch it, but then I get the penny and the penny does scratch it and leaves a mark on it, then I know it's somewhere here in between 2.5 and 3.5. Calcite's not going to be the only thing that falls in that range, but that really helps me narrow things down. So that's what you're wanting to do. You're wanting to start low and kind of go up with your tools or with other minerals and see, does this scratch it? Does that scratch it? Does this scratch it? No. But does this scratch it? Yes. Okay. I know it's in between a 5 and a 6. And so now I have this range, and as I go through my lab and I try to determine what mineral I have, if my hardness falls in between that range, it could be a possibility. If I think it's a mineral, but it says it's like a 9, but I was able to scratch it with a 6, then it's not that mineral. I need to go and find a different answer for this. And so you're looking for this range. So we have copper penny at 3.5, a wire nail at 4.5, glass. We have the glass plates here, and just like you do on the streak plate, just like you do on the streak plate, you're going to take your mineral and see if it scratches the glass. Don't hold it in your hand. These won't break often. These are actually pretty thick. I've used thinner ones. But you don't want it to break in your hand, so set it on the table, push down pretty hard, and drag it across the glass. It's going to sound terrible. It's going to be like nails on a chalkboard. But you got to know whether you're scratching it or not. Also, you can use a knife blade if you have a pocket knife, which you shouldn't, and don't bring one. If you need one, let me know. I'll get you something to use there. And then the streak plate is 6.5. And remember I mentioned some minerals don't leave a streak. Anything above a 6.5 just isn't going to leave a streak. It's going to actually scratch the streak plate itself. And any powder that you see will be left over from the streak plate and not the mineral. So looking at the minerals, we have calcite, we have fluorite, which is associated with fluoride, which we put in our drinking water and toothpaste and stuff. Apatite, which is like a black kind of mineral, and you're starting to get hard here around 5. Orthoclase and quartz, a 6 and a 7. Orthoclase is a type of feldspar, and quartz goes along with it in granite. So these are 2 of the 3 constituents, along with hornblende, which is also somewhere around here on the Mohs hardness scale. These are in granite, which tells you they're pretty hard. And so that's why we use them, is they're good for countertop surfaces. They're not going to be scratched easily. We also use them for building materials. You get up into topaz, which is a gemstone. Corundum, which somebody looked up for me earlier, which is rubies, and I don't remember the other one. But it's another really expensive, well-used gemstone. And then obviously diamond at 10 is one of the hardest natural minerals.
Isn't it garnet?
Yes, corundum is garnet and something else. So it wasn't what I said. What did I say? Rubies? Yeah, it wasn't rubies. It's garnets and, yes, somebody Google it. Corundum. Is it, what's the green one?
Ruby and sapphire.
Oh, sapphire, the blue ones, yeah. So red corundum are rubies and blue corundum are sapphires. And the reason your upper, maybe not quartz so much, but there is some quartz jewelry. The reason your upper minerals, especially if they're clear or transparent, are used as gemstones is because they're so hard, they're liable to last for a long time. If you pay a lot of money for it, you don't want it to like shatter the first time you hit a wall or a countertop with it, especially if you're wearing it all the time. You want to be able to keep it for a long time and hopefully have it appreciate. So one of your descendants can trade it in at Antiques Roadshow and get a bunch of money on it. So this is just a scale to show you. It's not quite logarithmic, but the hardness really goes up towards the end of the hardness scale. So talc down here is very, very soft. Gypsum, calcite, fluorite. When you get up to quartz, you're talking like many times harder than talc. And so quartz is actually a pretty hard material. We use quartz for, quartz is basically the main constituent of sand. So sandpaper, other abrasion materials, you're really starting out around here. Then you get into your gemstones, topaz, corundum, and diamond is just way harder than everything else. It's the way the molecules connect together that lends diamonds its hardness quality. Now we get to cleavage. How much time do we have left?
5 minutes.
5 minutes. All right. We can talk a little bit about cleavage. Cleavage is difficult to tell apart from your crystal growth habits because it's kind of formed in the same way. It's based on how the molecules connect together. So if I come back over here, this is just an example and not an accurate one for the one that we're seeing. But if you have linear molecules here, these bonds in between that molecule are going to be very difficult to break. It's going to take a lot of energy to break it in this direction. But as these molecules connect to other similar molecules, these bonds might be very weak. They could be an ionic bond. There's all sorts of ways that they can connect in weak ways. And so if I hit this piece or if I try to cut it with a knife, it's going to be much, much easier to cut along this plane than it is to cut along the vertical plane. And what that leads to is a tendency to break in a certain way, especially in flat planes. And so that's what we see here with cleavage. It is the tendency to break along planes of weak bonding inside of your mineral. What it produces is smooth, flat surfaces. If it's not smooth and flat, it's not cleavage. It falls under the category of fracture, which we'll see in just a second. So remember that it has to be broken. If it's grown that way in a flat surface, that's a crystal face, and that comes from crystal habit. If it's broken that way, then that becomes cleavage. Not all minerals have cleavage. In fact, I would say probably most of them don't. None of the metallic minerals have cleavage. It's usually only in your like silicate kind of minerals. So here's an example of some of them, and I will actually go, before y'all leave, we'll talk about this tomorrow probably. Before y'all leave, I want to show you, yes. Hello.
Hello.
Were you looking for somebody?
No.
Oh.
I didn't know. I didn't guess she didn't call you, but an ARD.
Oh, no, they didn't call. 9:15. I'm late. So we will pick up with this tomorrow, and we'll talk about cleavage and